Thanks for coming, everybody. So today's competition is Avito demand prediction. It's part of the Learn Kaggle series. So who are we? My name is Steve. I do data science at Dialpad. My background's in economics. I've got a master's in economics. And then I kind of started to learn more about data science and switch over careers. And I've been working with Justin on Kaggle competitions since February. So this is the second one we've done. And the first one we did was March Madness.
Hello, everybody. My name is Justin, and I'm a business analyst at Best Buy. I work with various different business units, such as store operations, logistics, and finance. And as Steve mentioned, I've been interested in doing machine learning and data science since February, and I hope to continue learning and growing in that space going forward.
Okay, so as some people kind of alluded to, this competition includes a lot of different types of data, including text, images, categorical variables, and continuous ones. So we're going to stay pretty high level and try to give you a good idea of the techniques used to address each of the different problems. The framework for today's agenda is I'll explain to you a little bit about what the competition is about. Justin will take you through what the data looks like. Then we'll go through the different types of techniques we use to get a good result with the different types of data, including the techniques that the winners used. And then finally, we'll give you what the top 3 solutions were and how they got to their final results. So the competition background. Matt already did a good job of telling you what Kaggle is, but I'll tell you a little bit more. So Kaggle's used as a platform where data scientists compete on data science challenges. It's sort of like one of the major hubs for new data science techniques and a good place if you're getting into it to learn supervised learning. Competitions can range from competitions where you get cash prizes, or there are competitions where you do just for learning. And the website has been owned by Google since 2017. So today's competition is Avito demand prediction. What Avito is they're a classified ads website. So you can imagine like a Craigslist or a Kijiji. And this image was posted on the competition. The intuition behind the challenge is that sometimes you get images which are bad quality, and there's some sort of idea that a bad quality image can influence whether an item will sell or not. And sometimes posts are, for the description, is badly formatted, and sometimes there's information there whether an item will sell or not. So combining all the different information regarding an Avito classifieds post, can we predict whether that item will sell or not? So here's an example from the Avito website. This is just like a regular person who went onto the website, tries to sell some shoes. Avito is actually pretty widespread. So in Russia, they're definitely the largest classified ad website. They get 22 million ads per day. This competition was posted April 24th, and then about 2 months later was the final deadline. So teams had about 2 months to get the results together. I'd like to hand off the rest of the presentation to Justin to talk about the data.
All right, so I'm going to talk about the data that was provided to us from Avito through Kaggle. So first, we're going to talk about the target variable, which we're trying to predict in this competition. Then we're going to review the evaluation metric, which was the metric used to score all the competitors and to determine who won. We're going to go through the data files and what was provided. We're then going to give brief information about the images provided, the categorical features, the continuous features, and the text features. So the target variable, which is the deal probability. So typically you would think that for a ad, you'd either sell it or not sell it, so it'd be a 0 or 1. But however, within the data, you see there's actually varying numbers. Some of them are 0 or 1, but some of them are also a fraction, like a decimal number. So in this competition, you're actually predicting Avito's own model about whether or not an ad would sell. So in this competition, you're scored using the root mean squared error. So with this, they're taking your predicted value against what really happened, squaring it, taking the sum, getting the mean, and square rooting it. One reason why they do this way is because the output of this is in the same units as your input. So in this case, the output would be in percentage points. So the data file. So you're given 6 CSV files. The first one is the train CSV. This is the main data set for training. The test CSV, this contains the information that you're going to be predicting against, and this is your predictions on this file is what you're being scored against. Train active and test active is extra data of other ads that were posted during the same time period as the first two. And the first two, you're given 2 weeks worth of listings. The periods train and periods test files are the date ranges when an ad was available for viewing on the website for all the previous files. So the train and test files. So you're given the item ID. This is a unique identifier for that particular ad or item for sale. You're then given the user ID. This is the unique identifier for the user that posted the ad. Then you're given the region, which can also be known as like the province if you're in Canada. This is the region that the ad was posted in. City is pretty straightforward. It's the city that the ad is posted in. The parent category. So this is the parent category that the ad belongs to for the item. And then within that, there's subcategories that subcategories for the item being sold. There's then 3 parameters, which are optional parameters that are created by Avito's model. Parameters called parameters 1, 2, and 3. You then provided the title that was provided by the user, as well as the description that they put in for the ad. You're given the price. The item sequence number, which is for a particular user, it is the post number for that one user. So if a user has 2,000 different ads, then they'll have, under their account, you have item sequence number 1 to 2,000, one for each of their unique posts. Then you're given the image. This image is the image ID number, which will map to the file that they've given us for images. And then image top 1 is a output of Avito's model trying to categorize that image in some fashion. And then you're given also the deal probability, which is only given in the train file, and this is what you're trying to predict. Oh, sorry.
I got 3 questions. Let's go.
So param 1, 2, and 3, are we looking at continuous here?
No, the categorical.
Okay, categorical.
Yeah, we'll go ahead that further on. We can talk about categorical variables. I turned it off.
Can you give an example of what param 1, 2, 3 are?
So I found some. I translated some of them. So param 1, I found things like pants, cell phone, like a lot of stuff like iPhone, or it was like type of automobile like a BMW or like a Lada. For parameter 2, it's more. It seems to be a subcategory of the first parameter. So there are things like red, blue, green color. And then the parameter 3, I found things to do mainly with clothing, things with sizes, like size like 42 to 50 or something like that. So they seem to be kind of subcategorizations of the main category for different products.
I'm going to wait until a few slides because I think you might answer my question soon.
Okay. So train active and test active are very similar, and they're the exact same style of data as the previous 2 files, except we are not given images, but you're given everything else. So in periods train and periods test, as mentioned before, these contain the data on when a post was active and when it ended.
Can you go back to the last one?
Sure.
I remember a few slides ago, there are the same number of columns for the train and the test. What's the difference between train active and test active?
That's a good question. I'm not actually sure. The data looks to be the exact same. They're giving you the same columns, the same data within all the columns. There's nothing really different between the two. It could be time frame. That's right, time frame. Train active was 2 weeks of data, and then the test data is actually, I think it was about 3 or 4 days. Starts 3 days after, and then there's a bunch of data for, and then you're predicting income in the future. So the train active is, data based on the same time period as the training data, and then the test active is active for the test data. So there's just a time period difference. That's right, now I remember. All right, images. So for this competition, you're given images for about 92% of the ads. All the images are JPEG format. You're, again, as I mentioned before, you're only given images for the listings in the train and test CSV files. You're only given 1 image per listing. And it was interesting to find that about a dozen of the files that were provided were actually corrupted, so you could not read them. All right, so we'll go over the categorical feature. Oh, sorry, go ahead.
What do you mean by corrupted specifically?
They had a file size of 0. There are 0 bytes in file size. So they were just nothing. All right, so categorical features. So here are the list of categorical features and the amount of unique values that were listed for each of these different features, as well as the amount null. So as you can see, as I mentioned before, how the parameter 1, 2, and 3 are kind of subcategories of the main category. And as you go deeper within the model, there's more and more null values, which makes sense because not all items will have all these subcategories and subcategories of subcategories within them. All right, so here I made a quick histogram of the categorical features for the regions. And as you can see, there's one region that kind of sticks out from the rest for the amount of ads being sold in that region. I am sorry, I can't pronounce that. All right, and now we're looking at the cities. So what I did is I took some buckets of number of ads and then put a count of how many cities were within each bucket. So as you can see, a majority of the cities have less than 2,500 ads, almost 95% or more. So what I did is I drilled down more into the 0 to 2,500 group and looked at how many, into just some smaller buckets. And as you can see here, actually, a lot of cities have less than 100 ads in that particular city. So here is the distribution of the number of ads by parent category. Again, there's one category that sticks out a lot from the rest in the middle there. And I took the opportunity here to translate them to English so we can actually read them. So that category is paraphernalia.
Sorry,
No worries.
can you go back a slide?
Sure.
Back another slide. Sorry, can you describe this one again? Number of cities.
Sorry, so the bottom here is the bucket. So 0 to 100 ads. 100,
Does that mean that
ads
there's 1,200 cities?
that have less than 100 ads that are posted in that city.
How many unique cities are there?
If you go back up, I think there's 1,700. 1,733.
Oh, wow. That's a lot of cities.
Oh, we're still here, yeah. All right, so then what I did is I took the category, and I did the same thing to the distribution of the top 20 categories by number of ads. And you see there's two kind of categories that are really high from the rest. I translated these, and the first one is clothing, and the second one is children's clothing. So obviously clothing is a very popular item on Avito. And here is the parameter 1 distribution, the top 20 by number of ads. So like I said before, that's kind of subcategory. So what I found is the very first one is women's clothing. The second one is girls' clothing, and the third one is boys' clothing. Oh, sorry, go ahead. I might have translated that incorrectly.
Actually, the most interesting one is fourth. Can you go back?
Number 4, yeah, that's selling, isn't it? It means selling?
It's just, yeah, it's just because all others are just like actually categories, and the fourth one is just basically sell.
Yeah, I translated. Yeah, I said it's just the word selling, so I don't know what exactly that means, what kind of category selling is, but because technically everything
Because
is being
I guess
sold.
it's all selling. There is no like renting because I believe that they have like a Craigslist. They would have like all kind of different things, and here it's only basically selling stuff.
True, I said because there's
And,
also like services. and
This
stuff.
fourth category doesn't make sense.
Yeah.
Yeah. Well, anyway, it's just a command.
Interesting observation for sure. Yeah, there's a weird kind of category in there.
So this was for param 1. Does param 2 and param 3 draw from the same set of categories?
No, param 1 and 2, sorry, param 2 and 3 appear to be subcategories of parameter 1. So it goes to a more granular level as you go into parameter 2 and parameter 3. Like parameter 1 could be BMW, then parameter 2 could be a red, and then parameter 3 could be two-door. It could be kind of getting progressively more descriptive.
For the ads that have parameter 2, do those all have parameter 1 as well?
I believe so.
Okay.
I think we've done this one already. Yeah. All right, so now we're talking about continuous features. So for the train data, one thing I want to mention, all the previous data I showed was only based on the train CSV. Which is a question.
Hello. Okay. So I just wonder like about the param 2 and param 3. It depends on param 1, right? So whether the type of param 2 and 3 change because of the param 1, like because you're saying that the first one can be like BMW and the second one will be like the color and the third one can be like two-door or like it's a SUV or something like that. But for clothes, the third one can be like size. So
Yes, that's right. It's different. So like for clothing, the first parameter, so the category is clothing, second parameter could be pants, third parameter could be color, then size.
So it can be changed. It can be like either
Yes,
numeric or category.
It appears to depend on the first category.
Okay.
Yeah.
Okay. Thank you.
Right.
Do you know if the ads have a single param 1, 2, and 3, or can it have multiple different types of?
Only one.
Okay.
They each have one each. They're unique. There's no there were no instances where you had like two parameter ones in the same in the cell. It's one only one. Okay. Also, items can only be in one category, so that's the same. The category is only one.
Okay. Thanks.
All right. So back to continuous features. So here's just a brief summary of the continuous features. What I find interesting for price, you can see that the max is really big. This up there with 80 billion for price, but the average is only 316,000. So there's some pretty far outliers out there for price. And also we find that about 5% have no price, they're null. And also, as you can see here for image top one, about 7.5%, so about 8% are null. The reason why they're null is because there is no image, so there is no image top, which is the category, which is a numerical categorization by Avito's model, but I don't know what the numbers mean. They're just a number of between 0 and 3066. All right, and then here are some of the text features, information about the text features. So for title, you can see here this is the number of characters that the title has, and also the description. So you can see some people are pretty concise with only 192 characters, but some people are pretty lengthy with over 3,000 characters in their description. And we see that 7% of the descriptions were null. All right, go ahead.
Okay, awesome. So next I'd like to talk about the different approaches people use to tackle the competition. So here's the 18th place team's diagram for what they did. Team name, We Had Great Fun. And you can kind of see that, maybe not so well from where you guys are, but at the very bottom of the image, we see raw image, categorical, continuous, text. And so this is kind of the system they use to combine this all into one probability at the very end. And we're going to kind of follow their architecture to look at how we can tackle different components of the problem. So first, we're going to look at images. So for images, there's basically two approaches. People either use a convolutional neural network, or they try to extract features using OpenCV. And so first, we're going to talk about extracting features with OpenCV. So if you're not familiar with OpenCV, it's a program, which is a library for Python also, that stands for Open Source Computer Vision. And it's sort of like the standard for manipulating images and doing things to images. So the third place team used these 6 features for images. The first one is dullness, which is really just a measure of how dark the image is. The second one is whiteness, which is a measure of how white the image is. I was trying to drill down and understand why these were not just exact opposites, but apparently they were not. The third one is uniformity. So how uniform an image is. You can imagine if someone posted like a red square and just a red square, the image would be very uniform, as opposed to something that was like very detailed where the image would not be very uniform. And the way they calculated this was using OpenCV's edge detection algorithms that's built into the package. The next one is color. Some people, you might have heard that you're more attractive when you wear red. And so maybe there's some sort of intuition when you're selling an item that if you sell like a red item or the image is more red, that there's something going on there. So the features they extracted were average color and dominant color. For number 5, they took the dimensions of the image. So the width and height uploaded, the file size of the image. And then lastly, they took blurriness, which is calculated by using something called the variance of the Laplacian filter. I don't really 100% understand how they figured it out, but there's a paper that was linked for how the formula works.
So these all make sense to me, like in that you can get one number or dimensions, you can get 3 numbers that come out of it. But for color, how do they, like, what is dominant color? Is it like category, or is it just like it's?
So I think that they're just extracting like the RGB of it, or like which one's more dominant, red, green, or blue. But they didn't go into more detail besides saying that they looked at average color and dominant color. Okay, so the third place team used those 6, but some other teams used an additional feature, which is key point detection. So here we have a picture of a man with a camera. And the idea is that when we have an image, that there are specific pixels in that image, which are the most interesting points of that image. So even if we invert it, flip it, turn it, those points are going to stay the same. And I believe the features that people extracted from the image using this method was like the number of key points and the location of key points. So is there a lot of key points near the center of the image? How many key points are appearing in the image when we use this OpenCV algorithm on it? And the next method would be convolutional neural networks. So I think that there's not a lot of value going to super deep detail on how this all works, but basically when you have a neural network, there's a specific type of neural network called the convolutional neural network, which can take multi-dimensional arrays, and you can feed it into the image and feed it into the model, and it will still retain positional information. So this type of network is very good at image problems and text problems, and it's been proven pretty successful for images, and it's like the premier image network. So most people used a CNN with a pre-trained model. There was a website called ImageNet, and a lot of pre-trained models have trained their models on ImageNet. So we can kind of leverage work that other people have done using these models that already have weights trained on them to apply to our problem, which is also an image problem. So it seems that we can use a lot of these pre-trained networks without having to go from a blank slate to extract features that are useful for the total problem. And pre-trained net models are also used later on for text models as well, mostly something called fast text, which we'll get into when we get to the text component of the presentation.
All right, I'm going to, excuse me, I'm going to talk about the categorical, how the different teams handle the categorical variables in this competition. So the first one was using count features. So this one is where they combine categorical and continuous features. For example, one of the different metrics they could have made was the number of unique sellers by city or region. This tries to get a sense of the amount of competition that someone has in a particular city or region. So you see how many other unique sellers there are, or how many other ads are in that same region or city. The other could be the mean or the min or the max of the selling price of a particular item. And it can go to the point of average selling price by category, by city, to see for this ad, where does it stand against other similarly categorized items for pricing, for a price point, to try to figure out if the probability of selling is based on where they sit in comparative to other substitution products. And the next is interaction feature. So this kind of goes back to what we're talking about with the couple examples I gave before with like the parameter 1 and the parent category. So they combine features like the automobile and then the make. So you have a BMW car, or you have a red BMW. So they combine these together to make a new feature by combining the two different categories together into one new category. And then they did this among different things with category and city, or the image top and city, or image top and category. And next we're going to talk about the continuous features and how they handle and use these. So most of them had to normalize data. So why do we normalize the data? Well, the first is there could be a wide range of variables, of variation in the variable, which could cause the objective function not to work correctly. And in this case, as we saw, the price had a very wide range of values. Also, then the next benefit of that is the gradient descent converges faster when you have normalized data. So what that means is that in this, we're trying to minimize the objective function, and this means that it gets there faster because it converges to that minimum quicker. So most teams used a form of logarithmic transformation on the price and the item sequence number, and those were usually the only two that they normalized in any fashion. Some of them normalized across all ads, while some of them tried to normalize across within the same category, or one of the optional parameters, like parameter 1. Usually parameter 1, since it had the least null values, parameter 2 and 3 had quite a few null values, so it's really hard to normalize against those, because over half the ads had no parameter 2 or 3. The next was missing values. So as mentioned before, the price had about 5% that had missing values. So there were several different approaches that teams used to handle this. The first one, which was very simple, they just took the average price for that category that the item belonged to, and that was the price they put into that for that ad. The next one was they created a model to predict the price. Usually they use a neural network or a gradient boosting model like LightGBM or XGBoost. And this one, they used a lot of the supplemental data to build a model, because that data has about 10 times the amount of rows than than your main data set. So they use it to build a new model to predict the price and then input those prices in. Finally, some teams, what they did is they created a separate model completely that omitted the price to predict the deal probability. And they then used this to predict the items in a test file that had no price, and only those ones, to predict the deal probability without using price. And the next feature that they created was using binning. So this is somewhat similar to what I did before with the cities and putting them into bins. So they use this as a pre-processing technique to reduce the effects of minor observation error. In this competition, there probably isn't much of this, but as an example of what this could be is, say you're trying to measure the temperature across the province, and you have thermometers all over the place, but they're different makes or models. So each one might have a little bit of error of measurement based on what the temperature actually is. So what they could do is they could bin them into temperatures, say intervals of like 3 degrees Celsius, and then have different intervals, and they bin them all together, and that tries to eliminate or tries to reduce the effect of the observation errors. Another reason is for statistical binning, and which is to group the number of features into smaller bins, and can also be used in multivariate statistics to bin several dimensions at the same time. An example for price was you could bin it into increments of, say, 25,000 up to 1 million, and then any category then the final category, will be anything that's greater than 1 million, and that tries to eliminate the effect of having like a price in the 80 billion having effect on your model.
So after you've been, were these continuous variables turned into categorical variables?
Yes, they would be.
And then did that make any difference, if they were used as a continuous or categorical?
This was mainly based on the winning solutions, and they didn't go into much detail how much effect this actually had. They just said that they did it, but they didn't provide the bins that they used, how granular or how big the bins were. For first, it's really hard to kind of say what kind of effect it did.
Yeah, so normally when I use kind of binning, it's when I have a distribution where the top end is hugely varied. So, maybe things make a lot of sense near the bottom end where like 1 to 1,000 make a lot of sense. But if I've got something like 80 billion in there, maybe it makes sense to have a bin that's like 5 million plus, because there's only like 10 items within that bin. So in order to try to get rid of and control crazy outliers, especially the end of your distribution, I think binning helps a lot there.
Is 80 billion a correct number for the price, or?
Yeah, so that's the number they posted for, yeah.
But is it correct, or does it suggest that the data is corrupt?
They're selling things like boats and mansions, so we think it's correct.
Actually, it relates to the fact that the currency exchange rate is kind of like, it's almost 70. There was a number 70 billion, so it's basically $1 billion. And maybe we're selling island or something like that, right?
I think that's exactly what it was when we checked it, right? Someone was actually selling like a lot of land.
I can't recall what the posting was for that one, but it could be they sell like services, they sell like land, property on here, so it could be someone's mansion on an island. They're selling it for 80 billion, which you said is about $1 billion US?
Yeah, that's $1 billion.
Billion US?
Yeah.
So maybe they're selling a castle on an island somewhere.
Would this be the channel that they would go through to sell?
Yeah, for the record, we don't think that item's sold.
It probably has a very low deal probability.
Probably throw it as like a joke, it's like a pencil or something. To kind of compare it, for the test data, the biggest value was 3 billion. So it's much less than the training data. I want to stay on this for a little bit longer. This is actually something I've not seen before, this whole binning. So can you also do you see an advantage to binning and then also treating it as a categorical? Oh no, sorry, as a like continuous feature and throwing that into your work. That's where I'm kind of a bit lost. Like I see this as just throwing away information. It's like only if you're treating it as a categorical variable, right?
So where I've kind of seen it before when I was in the economics world was especially when you had like large items and basically everything's a regression. Those items would like destroy your model. So a lot of times items past a certain value would get binned instead and turn into like a dummy variable or something.
I think this also happens to do with the fashion right now in Kaggle, which involves taking categorical variables and turning them into embeddings. Like FastAI kept on talking about it. So I'm guessing this is in part this, because the other thing you would do, which was previously mentioned, is the logarithmic transformation for price, which is what we'd normally see.
So in programs like Python or R, they have features like automatic binning, right? The binning depends on the precision of measurements and like in physics. Also, just making a comment, you don't want to make the bins too small, then your numbers in each bin will be very small, like 1 or 2, then you don't gain much information, and you don't want to make the bins too big, too large, then you will have also you lose a lot of information. So actually, these programs can find the right number of bins automatically for you, so that you don't lose, you gain the maximum information.
So you don't lose, you never gain information.
Well, you're losing information, but if you use a too small bin, then each bin will have 1 or 2 data points. Then you'll just, there's no point. Yeah.
And I think Stephen mentioned just now that it's just a way to control for outliers. Just because like that 80 million, like you can put it into one bin so that it doesn't skew your data completely.
Yeah,
right?
I see that. I see that argument. I fear it. Well, I can go on and on about this. Let's go.
So I've actually been doing this recently, and some ways you can do this is to basically sort of construct like a tree-like model, which will sort of it does the splits for you anyway. So say for like XGBoost will decide for that continuous variable where it thinks the split should be for that continuous variable. So you can look at what you're predicting on, and then just sort of training on that, and then hopefully that gives you like enough information. But as you say, like it's a way of just sort of doing it as robustly. But I've been looking at it because this particular type of model we were looking at will only accept categorical variables, and so there it's like you're just trying to convert it from a continuous to a categorical.
Sorry, one last thing. The one case where I've actually had an improvement in the model by binning things is when the thing that we're measuring is highly unreliable. So it could be like a 1 or it could be a 5. So if you just bin it just broadly, we found an improvement in predictiveness there. But with price, I don't know. It still seems like you want to do a logarithmic.
Is there like an optimal number of things you should be having in the bins? Clearly, like too small is bad, too large is bad, but what is that kind of potentially target number?
So you can simply do it by percentile to say like I want 25% in this, 25% that, 25% that. So that'll be like the simplest way. And then you can do it in a more sophisticated way, sort of tree-based method as well.
Okay, one more. And then go into drinks after. But I want to be the last to talk. So, Mike, just give me a head nod, and I'll say it. Are you talking about completely replacing the binning by using a decision tree that it kind of accomplishes the binning for you? Like, are you just doing a decision tree to turn it into a categorical feature? So there's still binning. Okay. And then finally, I feel like this is probably a good like ensemble approach. Like you're throwing some information away, maybe something that can give you some benefit, but let's just like do both options, continuous and, okay. Okay. Okay, one more Mahmood and then,
So I assume you're talking specifically about the price, the asking price, right? Here. And the target of the competition is to predict the actual price in the end. So I assume in addition to binning. No, predict if it sells or not. Only if it sells.
Okay.
okay, sorry.
Cool. So the next type of data is text. So for text, a lot of people pulled out really basic statistics regarding the text. So for title and description, how many characters, how many words, number of unique words, average post length within that category, average post length of that user. So those are the kind of numbers that people pulled out of the text. But we can go a lot deeper than that. So before the text gets pushed to a more complicated model, a lot of pre-processing gets done. And here are the kind of three major things that I saw for pre-processing that was done for text. So the first one is removing stop words. And if you're new to NLP, you probably don't know what a stop word is. So if you have a basic sentence like, my hair is black, right? Maybe there's some component of that sentence which I can take out and you'll still understand. If I said my hair black, I mean, I'd sound very primitive, but I think you would understand what I meant. And the idea is that a lot of these words inside of an English sentence or inside of any sentence don't really have a lot of information in them. So we can remove those words to speed up our model so there's less data, and remove those words so there's less noise. So there's lots of packages that can remove stop words for you. The popular one is NLTK for Python. The other thing is stemming and lemmatization. So these are kind of mutually exclusive. The intuition here is that if I had a word like run and running, they're separate words, but they have the same kind of intuition behind them. They have a similar meaning. So how do we join them to say that, when I say run and I see running in a sentence, they probably have a similar notion of what direction we're going. So stemming is kind of like a crude way of chopping up a word. So if I have the word ponies and I stemmed it, it would end up as PONI. But that's not really a real word. If I had a word ponies and I lemmatized it, it would kind of use some sort of pre-existing dictionary and change it to the base word of the word. So we would end up with like a real word, PONY, pony. There's advantages to both. So where lemmatization kind of falls apart is, maybe that word isn't inside of our pre-existing dictionary. So it makes sense to stem instead. And some people just don't do either of them. So, you always have those options. The major thing that I saw for text was people drawing word embeddings out. And some of the more veteran people here might have seen something like this before, where we have some sort of notion of what a word vector is. So a word embedding is when we have text converted into a numerical representation. And that can be shown in a lot of different ways. The popular way is here where we look at words in relation to other words so that we can have some sort of meaning behind them. And then we can add in some subtract. But this is not really the style of algorithm that we use to solve this competition. Really, the only part of this word embedding thing that was used to solve this competition was people extracting TF IDF vectors from the text. And so I'd like to explain what that is. It stands for term frequency inverse document frequency. And there's a lot of words there, but it's actually pretty simple. So term frequency is how frequently a word appears in a document. So if I have a newspaper and it's my document, and I want to see how many times the word Trump appeared in my newspaper, if it appeared 300 times, then my term frequency for that document is 300. Inverse document frequency is how many documents contain a certain word. So if I have 100 newspapers and 50 of them contain the word Trump, then I can calculate my inverse document frequency. So the log of total number of documents, which would be 100, over 50, which is the amount of newspapers with the word Trump in them, for a log of 100 over 50. And then we multiply those two ideas together to get TF-IDF, which is the whole thing. So here's an example. We've got two documents in our corpus, our body of works. We want to calculate what is the TF-IDF for the word messy in document 1. So the amount of times messy appears in document 1 is 4. The amount of documents that contain the word messy is 1, since document 2 doesn't have any occurrence of it. So we get total of log 2 total documents over one messy document for log of 2 over 1, and we multiply them together to get 4 times the log of 2. Let me just go back to this one for a second. And so the way that this was used was for individual important words, we get a very sparse vector representation of words that are important, and a lot of teams just extracted, looked for words that were important and had that word be a feature in their models. Sorry? They didn't normalize TF. You just have to straight count here before. Sure, yeah.
They didn't normalize TF. They just had a count there of 4, which means that if you filled your document with BMW 1,000 times, you'd have a higher score?
Yeah, so I mean, they definitely went deeper in how they use TF-IDF. I think some of them are normalized, some of them had additional things done to them, and most of these teams had many models that fed into one big ensemble. But for like the base level, most teams had TF-IDF in their model somehow. They didn't really have their kernels available, but in their explanations, that's kind of what they did. So now that we have...
Can I ask a question?
Yeah, sure.
Yeah. So can you go back to that
Sure.
TF-IDF? I just noticed that TF is just a ratio and IDF is a log. So maybe, I don't know, maybe it's better to have both of them in log and then just add them. Would be kind of more consistent, I guess. But that's maybe a small difference.
I don't think that was very effective. But if you want to And to your question at the back, I've done a lot of NLP stuff. What you brought up is a good point. There's a lot of different tricks you can do with that first number, term frequency. Sometimes people just use like a binary count. So like if it appeared or not, it's a 1 or a 0 sort of thing.
Yeah, so it looks like we have some rough idea of how teams tackled each individual data type. And so here's the 14th place team, the Almost Golden Defenders. What they did, now that we have all the different data types in some sort of model, the way that we combine all these models is they use something called blending and stacking. And so we're going to talk about the different ways that people combine their various models at the very end of the procedure. So when we combine models together, it's something called meta-ensembling. The most basic type of meta-ensembling is voting. Imagine we have a classification problem when we're trying to figure out, hey, is this car red or blue? And then we have 3 models, and 2 of them vote blue, 1 votes red. So the final ensembled model would vote blue. And that's like a simple way of how voting can meta-ensemble. Other ways we can do this are averaging. So if we have like a regression model trying to predict the price of, we've got 10 different models predicting a price. A simple way that we can combine them is just taking the average. And then a more complicated way is stacking and blending. And they're a little bit different, they're a little nuanced, but basically what it means is that we have a bunch of models and they feed into other models as features. So we have, let's say, if we go back here, all these level 1 models will become features for these level 2 models, and then we can go several layers deep until we get our final result. And the most popular type of meta-ensembler that I saw for this competition was XGBoost and LightGBM. These 2 models were actually used at various stages throughout most people's framework. So it could be as a level 1 model, it could be as like the final model. And these are kind of like the 2 premier gradient boosting libraries. Both frameworks were used by most teams, and some teams just use LightGBM. And the kind of intuition behind how these are working is that these are based on a decision tree. So we have our first decision tree, and a sequentially next decision tree, which tries to train on the errors of the previous one. And then we go many iterations deep, and then we get ideally an accurate result. And so I've kind of listed the documentation for both of these frameworks here, and they're both free and open source. So lastly, we have the summary of the winners.
All right, so here I'll quickly describe the leaderboard and the prizes. So for the prizes, there was 12,000 USD for the winning team, 8,000 for the second place, and 5,000 for the third place, for a total of $25,000 in prizes. And to the right here, you can see the leaderboard. So the top team won with RMSE of 0.215, which means that on average they were off by 21.5% from the actual. And the scores are actually very close. So the top team had 0.215, while the 19th team had 0.2197. And there's actually quite a few. I think there was almost 700 people in like the 0.22 to 0.21 range. It was like a lot of people in that that range was very close for scores. Go ahead.
So we'll go over the.
Sorry, did some of these teams kind of like, was there any comments about if they knew each other or anything like that? There's a surprising number of team names revolving around dance, like at least 4 of them.
I'm not sure.
A lot of these teams were already doing well on leaderboards, and they came together afterwards.
Oh, okay, cool. So you're allowed to do that kind of thing? Like
Sorry?
You're allowed to form a team later, I guess?
You have up until a week before the deadline to do your final merge.
Yeah, it was on the previous slide. So I think June 20th was the final deadline for team formation and merging.
So the third place team, which I love their name, is Supernova. What they did was they had a 2-layer stack, and then they blended the rest of their models, and it was an ensemble of 2 models. But the interesting thing they did was they treated the problem as a time series problem. So they looked at the first 6 days, and then the last 4 days as their validation set, and they tried to mimic the difference between the actual training set and the test set for time. And so they did very well doing that, and they used a bidirectional GRU. But it was one of the few teams that I saw that kind of treated the problem as a time series problem. Really interestingly, they kind of discarded the days in between the first 6 and the last 4, so that they ignored part of the data. The other interesting thing they did was for description and title, as opposed to doing NLP on both components, they just concatenated them and treated it as one feature, and did all their models on just one combined set of text. The second place team, Song and Dance Ensemble, people are saying that this was the deepest meta ensembling level. They did a 6-layer stack. And so they had a very complicated architecture. And they used a bunch of simple models, which other teams didn't use. So most teams relied on for their base models. They still use like GBM for their base models or a neural network. This team threw in a lot of smaller, less powerful models in there. So they had like ridge regression, a lot of linear regression in there. And then they relied on the pre-trained image features, just like everybody else. Finally, the first place team, they had 4 people on their team. The interesting thing about this team is that 2 people on the team were solely dedicated to feature engineering, and they feature engineered right up until the last day. They said that on the 3 days before the competition ended, they were still feature engineering and found the features that were good enough to push them over to first place. So this image here that you see is just one of the models of one of the modeling guys. The other guy who was also modeling didn't post a diagram of how he did his stuff. But yeah, the majority of the work for this team was all feature engineering. And all the features that we talked about today in like the text, image, the data binning, they did it all. And a lot more that we didn't cover. So here's just a zoomed in version of what one of the modelers did before they ensembled. And that's it.
All right, well, thank you very much, everybody, for your time, and I hope you can use the information provided here to help you if you guys want to take part in the competition, and hopefully it was insightful. Thank you very much.
We've got time for questions.
Do you have any idea how the deal probability was measured in the trained data?
Yeah, so a lot of people were asking, how is it possible for somebody to 0.7 sell an item? I think what's going on, Avito never came out and said, is that if you're using information regarding the communication between the buyer and seller, so like the message history, to have a model to predict whether a transaction occurred or not. So I think that's what's happening, and that information was not privy to us. So I think that we're actually predicting the model that they're using based on the conversation history.
Two questions. First, how many languages were there? Was it only Russian?
It was only Russian.
Okay, only Russian. Second question, I missed it. Do we have information about how long the sale took to complete?
Yes, in the period train and period test data, it had the date that the post was created by the user, but then it also had the date that it was active for sale. So, and they didn't necessarily need to be the same. So a user can create the post now, but have it available next week. So it had the date it was created, the date it was available for viewing, and the date it was off the market. Yeah, that was provided.
Can you go one slide before? So I'm actually curious about how the winning team do the categorical embedding. For how do they embed the category features?
They didn't. Well, they described how they said that they created, they did the categorical embedding, but they didn't provide a lot of detail into exactly how they did it, and they didn't provide. I don't believe the kernels were available either, so we didn't have a chance to like dig through the code to see what they did either.
They could have just done something simple, initiated it randomly, and let the errors kind of backpropagate. If this is all just one big network, which it looks like it is, then you can just initialize the embeddings randomly. I don't know if this is what they did. You can just initialize them randomly, or with word to back. Shoot. I guess the point that I was trying to make is one possible approach is they could just initialize it randomly. Because this is all one big model, the errors will propagate like all the way back to those embeddings, possibly.
So there's a fast AI package that actually has this type of categorical embedding right out of the box. I'm going to guess they probably did that. They basically just treat categories like words for a word embedding. That's how it works.
So based on that picture, it's only neural networks were used for first place, and the second and third, I guess, they're used like different other methods for ensembling, right? So did they mention like anything else, or they said that actually that's what they used, and this is like a final solution?
Yes, this is not their final solution. This is the model that one of the modelers built, and he worked on just neural networks. There's a lot of XGBoost and LightGBM in there, and we didn't have a diagram for like the whole thing, but I'm sure that there was a lot of models.
That's just a part of the ensemble then. That's just a part of the ensemble.
Yeah, I think it's just part of the ensemble.
Okay, cool. Thanks.
I have a couple questions. You mentioned earlier that people were using Word2Vec for their word embeddings. Do you know if that was just using a pre-trained Word2Vec embeddings, or if there was a lot of data that was given, 15 million different ads? Did anybody just train their own Word2Vec based on those ads?
So most people used a pre-trained fast text model. So pretty much all the top 25 used fast text.
Fast text is.
I guess that's based on the fact that this is Russian-speaking segment, and then I guess that's from Facebook, right? The fast text, yeah.
Yeah, that's right.
So it just has a better corpus of data for Russian. That's it. Yeah, than Wikipedia or whatever Word2Vec is trained on. Is it?
Yeah, I mean, there's a lot of different Word2Vec kind of pre-trained models. Did you have a question?
Mostly in English.
Yeah, mostly in English. My second question, you guys competed in the competition, but we didn't hear much about your approach. Do you want to just like, unless it's too embarrassing.
Yeah,
like.
no, there was like a lot of us working on this one, and we did not do very well. I would say that based on like, we're like in the 0.23, we're doing pretty well, but everybody was in the 0.23. It was all the decimal places afterwards. And so yeah, we didn't do great.
What approach were you using?
So we had different team members that focused on different components. We found some really sketchy Russian pre-trained word embeddings, which we tried, and they didn't work so well. So we trained our own word embeddings on the text. We had a lot of image features which weren't very useful. So I guess the most useful variable in the whole data set was the image top one that represented like 90% of the explanatory power for all teams. And that's like the model that was built by Avito. So if you have that in there, everything else is just really small percentages, and it's really hard to gauge when it's actually useful.
Yeah, that's one of the things about these competitions is like some guy that's doing really well will post some of his solutions, and then just everybody will use that, and it's just like impossible to make any gains on this. Like,
I believe, right, if I recall, the third place solution did that. They used a portion of someone else's code.
Yeah.
And they modified it.
Yeah, so the image features that we showed earlier from OpenCV was posted by some guy who I think didn't even send a solution in. but everybody used his features.
So any other questions?
Did any team use data augmentation?
Data augmentation? I don't believe so, no.
For the CNN, almost certainly, because it's just
right. But we don't think that they like oversample or like change the sampling rate or anything like that to create more data.
Yeah. Okay. I think that this is the end of the questions. So let's give them a big round of applause.